Welcome back to this channel for practice problems for actuarial exams. My name is Krzysztof Ostaszewski. You can find information about me at smarturl.it/Jedi. My advice on how to pass actuarial exams is at smarturl.it/pass. I direct the actuarial program at Illinois State University. You can find information about it at smarturl.it/actuary. If you would like to make a tax-deductible donation to support our students, please go to smarturl.it/help ISU Actuary. This is problem number 1 from the written answer part of the Spring 2018 exam MLC, and it is a practice problem for exam LTAM. In this problem we have an entity, TCFA, is a firm with two categories of employment, active and inactive. You are using the following Markov model to project employment at TCFA, where the states are 0 for active, 1 for inactive, and you can move from one state out to the other in both directions. You are given the following additional information: that the force of transition from state 0 to state 1 is constant, equal to 0.2, and the force of transition from state 1 to state 0 is constant, equal to 0.1. All new hires are in the active state. TCFA pays a rehiring bonus of $10,000 at the moment of rehiring when an inactive employee becomes active. Only one bonus is paid in each year at the time of the first transition back to the active state. Delta, the force of interest, is 0.05. Part A, show that the probability that an active employee becomes inactive at least once in the first 7 months is 0.11 to the nearest 0.01. You should calculate the probability to the nearest 0.001. Part B, Part 1, show that the probability that a newly hired employee has made one transition to the inactive state and has not moved back to the active state by time t is 2 times e to the minus 0.1t minus e to the minus 0.2t, and 2 is multiplied by the difference of the two quantities. Calculate the expected, part 2, calculate the expected present value of the rehiring bonus for a single employee during the first year of employment. We continue. TCFA has now decided to change its employment practices as follows. An inactive employee who has transitioned only once is eligible to return to active employment and has a force of transition for such return of 0.10. The force of transition from active to inactive is 0.20 for both the first and second transitions to inactive. Once employees have become inactive for the second time, they are no longer eligible to return to active employment. Part C. Draw a diagram of a 4-state Markov model that could be used to model employee transitions following the change in hiring practices. You should define the states and write down the values of all non-zero transition intensities. Part D. Use the revised model to calculate the probability that a newly hired employee is actively employed at the end of 5 years. And here's the solution. We begin with Part A. The probability that an active employee becomes inactive at least once in the first 7 months is the integral from 0 to 7/12, 7/12 of a year is 7 months, of the probability that this employee, starting at age x, over time t, remains in state 0 continuously, and then at age x plus t, time t into the year, it transitions into state 1 instantly. And we add up all such probabilities effectively through the integral from 0 to 7/12. And of course, once this person transitions, we already have what we want. So we don't care about possibly other future transitions because it simply says becomes inactive at least once. That's equal to the integral from 0 to 7/12 of e to the minus 0.2t. That force that we put in there is the sum of all forces for going out of state 0, and you basically avoid going out of state 0, well, that sum is just 1/4 of 0.2, multiplied by the force of transition out of state 0, which is into state 1, which is 0.2, but it's the same because there's only one force. And of course, if you take a closer look at this expression, this is simply 0.2 times a bar angle 7/12 at delta equal to 20%. So this must be equal to 0.2 times 1 minus e to the minus 0.2 times 7/12 over 0.2. And we just calculate it to be 0.11011,823 approximately. For part B, the probability that a newly hired employee has made one transition to the inactive state and has not moved back to the active state by time t is, well, the integral from 0 to t of first remaining for time s in state 0, then transitioning into state 1 with force mu 0, 1, intensity 0, 1, and then remaining in state 1 until the end of the period for a period of time of length t minus s. And remember, you always calculate the probability of remaining continuously in a certain state as e to the minus the integral of the sum of the forces that take it out. In this case, forces are constant, so it's just you need to figure out the sum of the forces taking it out, and that sum is 0.1 over a period of time of t minus s, so the integral would be an integral of a constant of 0.1, so that's just simply e to the minus 0.1 t minus s. In the same way, the first expression is e to the minus 0.2 s. We write it all out. Then this becomes simply 0.2 t times e to the minus 0.1 t times a bar angle t at delta equal to 10%, because we would end up with having e to the minus 0.2 s times e to the minus to plus 0.1 s, so that's why you end up with e to the minus 0.1 s. And of course, a bar angle t is 1 minus e to the minus 0.1 t over 0.1. So 0.2 over 0.1 is just 2, and we end up with 2 times e to the minus 0.1 t minus e to the minus 0.2 t, which is exactly what we wanted. For the second part of part B, we calculated the expected present value of the rehiring bonus for a single employee during the first year of employment. So the present value of rehiring bonus is 10,000 times e to the minus 0.05 t, assuming rehiring at the moment t, and we're doing the integral from 0 to 1 for all possible values of t. Then we multiply this by the probability calculated in part B1, which is the probability of this event that we're calculating it for happening, and we only look at one such event, times 0.1, which is the force of transition from state 1 to state 0. That simply is, if we multiply it all out, that becomes 10,000 times 0.1 is 1,000, times 2 is 2,000, integral from 0 to 1 of e to the minus 0.15 t minus e to the minus 0.25 t, and that's 2,000 times a bar angle 1 at delta equal to 15% minus a bar angle 1 at delta equal to 25%. So we just write out the formulas for a bar angle 1 with both forces, do the calculation, and it comes out to be 87.6332456 approximately. For part C, we have 4 states because we adjusted the states for the new policy of the company. So state 0 is always active until now. State 1 is first time inactive. State 2 is previously inactive once but now active, and state 3 is inactive second time and thus ineligible to return. And this is the diagram of what can happen. You can go from state 0 to state 1, from state 1 to state 2, and from state 2 to state 3. And state 3 is absorbing. You don't get out of there. And we now use the revised model to calculate the probability that a newly hired employee is actively employed at the end of 5 years. That probability equals the sum of two probabilities, that such an employee is actively employed continuously for 5 years, plus that such an employee became inactive once during the 5 years, but returned to being actively employed by the end of the said 5-year period, and once returned to it, stayed in it till the end of the said 5-year period. Let us write TPX01, no return for the probability that a newly hired employee has made one transition to the inactive state and has not moved back to the active state by time t. And we actually calculate that probability in part B2 as 2 times e to the minus 0.1 t minus e to the minus 0.2 t, because the model, as far as just original state 01, is unaffected by any adjustments. I probably should say that the model in the context of the event that we're calculating. So the sum of the two probabilities that we're calculating, or that we're looking for, is 5px00 with a bar above 00, meaning continuously remaining in that state. And the state of transition out of it is 0.2. So this is just going to be, it's a constant force, so it's going to be e to the minus 5 times 0.2, which is e to the minus 1. And the second part is the integral from 0 to 5 of tpx01 no return times mu at x plus t with the force 1, 2, going to state 2, times 5 minus t px 2 bar. We have to remain in state 2. Not go to state 3. Okay, well, so it's e to the minus 5 times 0.2 plus integral from 0 to 5 of 2 times e to the minus 0.1 t minus e to the minus 0.2 t times 0.1. That's the force of transition from state 1 to state 2. And the state of transition out of state 2 is 0.2, so this probability of remaining in that state is e to the minus 0.2 times 5 minus t, because that's how long the interval is, constant force 0.2 dt. So that's e to the minus 0.1 plus 0.2 times e to the minus 0.1 times the interval from 0 to 5 of e to the 0.1 minus 1 dt, which then we calculate as e to the minus 0.1 plus 0.2 times e to the minus 1 times the integral from 0 to 5 of e to the 0.1 t dt minus, integral from 0 to 5 of 1 is 5, multiplied by 0.2 is 1. We have a minus in front of 1, so that's why we get a 1. So it's minus e to the 0.1. Oh, the e to the 0.1 cancels, and this becomes just 0.2 e to the minus 1 times s bar angle 5 at delta equal to 10%, which is 0.2 e to the minus 1 times e to the 5 times 0.10 minus 1 over 0.10. Okay, 0.2 over 0.10 is 2. And then we have e to the minus 1 times e to the 0.5 minus 1, and that's approximately 0.4773024. Please remember this is copyrighted material. The problem itself belongs to the Society of Actuaries. The solution is mine. Good luck in your studies and good luck on the test.